Hello everyone. Today we are going to understand the linear system from the vector perspective. Let's look at this linear system example. We can rewrite the linear equation like this, where each column in the coefficient matrix are the coefficients of the unknowns in the linear system. Treating each column as a vector in the linear system, we can use vector a1, a2, and a3 to represent the three sets of coefficients, and vector b to represent the right-hand side of the linear system. Eventually, we can express the linear system as a vector equation. If we swap the left-hand side and the right-hand side of the vector equation and treat x1, x2, x3 as the scalars of a1, a2, and a3, then vector b can be treated as a linear combination of a1, a2, and a3 if x1, x2, and x3 can be found. Solving the linear system now becomes a problem of finding the scalars of the three vectors a1, a2, and a3 that form up the vector b collectively. In this example, using Gauss-Jordan elimination, we can get a unique solution with x1 equals to 2, x2 equals to 1, and x3 equals to 4. That holds the equation. We now can confirm that vector b is a linear combination of vectors a1, a2, and a3. We might have a question here. What decides whether vector b is a linear combination of a1, a2, and a3? The answer actually does not depend on the vector b itself. In fact, b can be an arbitrary vector but still be a linear combination of a1, a2, and a3 in this example. Let's use star to represent an arbitrary real number and apply Gauss-Jordan elimination on the linear system when b is an arbitrary vector. The result shows there will be always an unique solution responding to the arbitrary vector b that holds the equation in this example. In other words, an arbitrary vector b can be expressed as a linear combination of the vectors a1, a2, and a3. In this case, we say a1, a2, and a3 span a three-dimensional space. Let's visualize this example in a three-dimensional space. Suppose b is 9, minus 1, and 18. We can find the responding vector 2, 1, 4 to hold the equation. If b is 2, minus 8, and 4, we can find the responding vector minus 1, minus 1, and 2 to hold the equation. In fact, for any arbitrary vector in a three-dimensional space, we can always find a unique solution in the same space to hold the linear equation. Thank you for watching the video today. Please subscribe to my channel and stay tuned for more interesting content.